everybody. I realize I'm standing between you and lunch. So I'm gonna do it as short as possible. So let's get started. Ruby 1.8 is slow because it's interpreted. But surprise, Ruby 1.9 is interpreted too. Thanks. Any questions? I'm just kidding. As already introduced, I'm the Konstantin with that horribly long Twitter handle and on GitHub. So, you know GitHub, the major sticker producer? They also, on the site, they also do code hosting. And I'm RKH on their code hosting website. I'm well known for like my 15 minutes of fame where when you did a Google image search for bike shedding, the first face that came up was mine. Besides that, I'm also the maintainer of Sinatra and contribute to some other mostly Ruby-related open source projects. And together with Alan Harris, I also wrote a book on Sinatra, which you can use that discount code, and then you get 50% off the ebook, which is like $6.50 US. That's approximately €3. So. And for a living, I live off donations. I'm working on a project called Travis. It's a hosted CI system, not to be confused with Jenkins. Where's that? Yeah, Zed was going on about how terrible Travis is yesterday, and after a while we realized he's talking about Jenkins. And currently we got some companies and a lot of actually private people just giving us money for working on our product, which we will launch a paid version for private repos soon. And we have a beta, basically the whole system, except you don't pay. And if you want to get onto that, you have to send a cat picture to support@travissci.com. And the best cat pictures will get instant access to the system. And that's our glorious team. Josh will be talking later, hopefully wearing his onesie. But let's get to the talk. I'm going to talk about Ruby. And I'm going to talk about Ruby internals. And this talk is mainly about performance. And I have to warn you, it's a highly technical topic, and we'll look at different Ruby implementations. So I hope you're all aware that there's more than one Ruby implementation, since Ruby is the language, but also the program that actually translates that language into machine instructions. And any guesses on how many Ruby implementations are out there? Just scream numbers. 50 was close. I counted 59. Those are not all usable. Some are more to what we expect Ruby to be, some are less. What we expect Ruby to be, one is completely fake. But I'm going to focus on the three largest ones on here, which are the three Ruby implementations that I would recommend you use in a production application. There's Ruby 1.9, MRI, the reference implementation, JRuby based on the Llvm, and Rubinius. I assume you probably all have heard of them to at least some extent. And what we're going to look into is specifically the method dispatch implementation on those Rubies. We're going to start with how the method dispatch is implemented in general and how methods are executed while looking at MRI. Then we're going to talk about inline caches and jitting on the example of Rubinius, and we're going to talk about Invoke Dynamic with JRuby. It's not that only these implementations are doing that. For instance, JRuby is also doing inline caching and jitting. But I just want to give you a feeling on what's going on under the hood. And we're going to look at this code, specifically the method, the body of the method, ultimate answer. And while looking at that, we assume that this method is called with the argument 42. So this is a really handy method. I hereby release this as public domain. You may use that in your code. And so what it does, it checks if the argument is the ultimate answer, and it accepts both a string or an integer. That's technology at its best. One thing you have to know about decent Ruby implementations is they just love bytecode. Just take the line value to S, and so the bytecode is actually just bytes that are basically instructions. We're going to go through it later on, but there is a textual representation, kind of the assembler of bytecode for all of those implementations. And for instance, on MRI, it looks like that. You have value there, and you send 2s to it. On Rubinius, it looks like this. They actually use an integer for identifying the local variable and send 2s to it. And on JRuby, on the Llvm 1.6, it looks like this. I removed some stuff here, and some stuff there, and some stuff over there. And if you look at all that and you've never seen something like that before, you're probably like, I have no idea what's going on here. So, quick reminder on VMs in general. You start with a source code file, a source code that's usually a text file. You run it through a parser. The parser on all those implementations creates a parse tree from that. And you can either walk that parse tree. It's basically similar to S expressions. It's just here's the operation plus, and there's those arguments. And the arguments can in turn be an expression again, etc. And you could walk that tree directly with an interpreter that then issues CPU instructions, or basically just runs code. That's what 1.8 does. Turns out this is rather slow. Or you could generate bytecode, which is kind of what we just saw. And then you have a bytecode interpreter that just basically is a while loop and says, get the next byte, and then it's a case statement. If the byte is this, then do that. And that, again, translates into CPU instructions, which is why I said in my second slide that 1.9 is interpreted too, because it's going the interpreter path. Or you could JIT it, which basically means generate machine code for that, like you would when you compile a C program. Then from there on, you can just run the machine code without any overhead, which in theory is as fast as compiling C code. In some theories, it's even faster, but usually it's not really that, but well. So, and the plan that we have when we want to call that method is, we are now Ruby. So we have to find that method, and we have to execute that method. But we want to do it fast. So what can we do? Well, we can find the method faster, and we can execute the method faster. It's easy as that, done. For finding faster, there are different techniques. There's the inline cache, also known as call side or send side cache. You can do lookup cache. You can do inlining. And then once you have it found really fast, you want to execute it really fast. You can actually reduce the operations, which is something MRI is experimenting with. Like instead of having one bytecode for pushing a local onto the stack and then one bytecode for calling a method on it, you can instead have one bytecode for pushing the first local on the stack and calling a method on it, which will reduce the number of loops you have to go around in your while loop. You can do just-in-time compilation. We'll talk about that later. And one of the main things you can do that really, really helps for executing faster is actually searching faster. Because searching for the methods that you have to call is one of the things you do a lot. Like all the Ruby code you write is basically just calling other methods. So if calling methods is fast, then your code is fast. Let's have a look at MRI. In MRI, a method internally is, if you want to search for a method from, say, C code, you can call RB underscore method underscore entry, which is basically you hand it a class and a method name. That will then call RB underscore method underscore entry method underscore without underscore cache, which if it hasn't cached it, so that's basically a lookup cache implemented right up here, and then that in turn will call the internal Ruby internal C method in Ruby search method, which actually has the lookup we are all used to. Like if you call ultimate answer, then on that class, then we'll look. Has that class, the method, and go up the inheritance chain. And that method looks like this. You get the class, which also can be the singleton class. You get the class here, and the ID is the C representation as its identifier, but it's basically a symbol, which is the name of the method. And then it goes up the inheritance chain. By looping through the classes. It basically just takes the method table and uses the superclass if it's not found, and then it returns the method entry. And that's the code that we need. So now we found the code. Now we have to run it. So that will be handed at some point to VM call 0. You don't have to understand all that code. I just want to give you a feeling on how Ruby looks internally. This is basically one of the main ideas, is looking into it. And you hand in the method entry, lots of stuff happens, and down here it's executed with VM underscore exec, and what that actually does is for the current bytecode you have, basically this again switch is the while loop, just it doesn't use while, it uses go to again from nested switches, which is really easy to understand, right? What it then does, when you call VM exec, it looks up the current bytecode in an instructions file, instructions manual, which basically just lists this bytecode does actually do the following stuff. A definition could look like this. This is actually the definition for send. There's a lot of other stuff, like it's taking stuff from the stack, etc., etc. The interesting thing is that this, again, as you can see here, is triggering a new search for the method you're actually sending, and then uses the call method macro for triggering the whole thing again. So you see it's basically just doing the same thing, search, execute, all the time. That is the heart of Llvm, the 1.9 VM. Okay, still following? Yes, okay. Scream at me if it's all too, or if I should go faster. Faster, anyone? Okay, Robinius. Robinius has the nice advantage of you being able to play with all that in Ruby. So you actually can access the method table in Ruby. Looks like this. Every module, we saw that in the talk just before this, has a method table. And that method table is kind of like a hash, but more simpler, more low level, that has buckets, basically hash entries, which then have the compiled code as objects in there, which was we saw that in Brian's talk, it was the return value of the def statement. And you can actually implement the lookup in Ruby. So if you want to search for a method on an object, you can ask it for its singleton class, and then you just go through basically the same code we looked at on MRI. You can just do a while. You can just go through the classes, through the inheritance chain. You have to call direct superclass because you also want to include modules that might define the method. And then you can just do the lookup on the method table. And then you also have the method object, which is, you would never do that because there are higher level methods where you can just say, give me that method instead of having to search for it. But this is to give you a feeling like what kind of introspection, reflection you have available. And then when you have the method, you can actually play around with it. So you can just ask the deep thought class for the method ultimate answer. The CM now is the compiled code. It used to be compiled method, but I just learned it has been renamed. And then you can do stuff like decode it, which will give you that output. It's basically what we already saw in Brian's slides. You can also ask it for the opcodes, which actually corresponds directly to the bytes you will have in the like if you write out the compiled file or look at the memory, those will be the bytes that will be stored there, and those are like 20, 0, etc., corresponding to this. And then you can also ask it for its literals, which is 2s, 42, and equals. So, but how does that work now? What is actually happening in the VM here? So let's go through this. Let's rearrange this. The literals are now up here. These are the bytes. These are the locals, so value. It's 42. In our example, that's the argument that's passed in. And if we rearrange the bytes to look like this, then they correspond directly to the decoded version. So the first byte is the byte 20. And the VM will take that byte and see that 20 corresponds to the instruction push local. And also, push local takes one argument. So it reads in another byte, which is 0. So it says push local 0, which means push the first local. The first local is value, so 42. So on the stack, we now have 42 because it's being pushed onto the stack. This here is the stack. Imagine it like an array, or like, well, it's a stack, push and pop array. Then it reads the next byte from the instruction stream, which is 49, which corresponds to send stack. And then that takes two arguments. The first one is the index of the literal. So the first literal is 2s, and the second one is the number of arguments that are passed onto that method, which for 2s is 0. So it's going to pop off 42 from the stack and push onto the stack the string version again. And the next instruction is 7, which means push literal. So the second literal, which is 42, will be pushed onto the stack. So we now have 42 and 42 on there. Also, it's going to call dup on that literal. Like this literal is really the string 42 in the method body. And imagine like returning that, and every time you call the method, the string has to be duplicated, because otherwise if you modify it, you would also modify it for any subsequent call to the method. So that's why this is happening. So the stack still looks the same, basically, and then there's an operation which optimizes the equals call, so it's usually so there can be better, easier optimizations. It will pop off 2 arguments from the stack, so the stack will basically be empty, and then it pushes on true, so on the stack is true, and then byte 11 says, whatever is on the stack right now, please return that. And then we're done. And found out that 42 is 42. If you imagine that as the bytes in memory, then the literal in place, like you have that line push local and then send stack to S. Then if you access that from the compiled method, there will really be the symbol to S. You could also replace it in the running process and basically change the method, because that's all live objects. So there's a 2S in there in memory, but upon the first call, that 2S will actually be replaced by an inline cache to make the call to S faster, again, to make Ruby code run faster on Rubinius. And it basically just stores the lookup. It knows what method has been called, so it knows the class that came in is an integer, and the next time we see an integer, then I already have 2S here and don't have to search for it again. There's more optimizations or more stuff in there, because it has to make sure that when it sees an integer, that actually 2S has not been redefined on integer. So basically any snapshot of a class is its own type, basically. And the inline cache also references the code to run as the initial code, the unoptimized code as the initial backend, and I'm going to talk about this in a second. So basically the inline cache knows this is the code to run, and it also knows this is the original code and we can have any other version now, and then it just checks, is everything still okay? Okay, let's go in and run that. And that's basically it. Yeah, and it takes care of caching that for multiple different classes. So it optimizes for integer and it can optimize for string. Right now it optimizes for 3 different classes. So it will be a really, really fast dispatch as long as there are just 3 different kinds of objects that are always passed to that. And that optimizes most of the code really, really well. And what it also allows you, since you reference the code at that point, it allows you to actually change that code, modify it, replace it with something else, with a specialized method. That specialized method can actually just be the cached bytecode, which is more or less the default. It can also be the bytecode inserted with breakpoints. And this is a really cool thing, because if you set a breakpoint in that method, then the referenced compiled code will be different, but the rest of the system will still stay the same. That way, you can have a debugger enabled in Rubinius and still run at full speed, which is a thing you cannot do on MRI. If you turn on the debugger on MRI, everything will be slow. On Rubinius, only the method where the breakpoint is, where you want to jump in, that is slow. And then as long as you continue stepping into the next method, it will again use the unoptimized version, and that will be slow. But as soon as you say like continue, it will be fast again. Can also be specialized for arguments, which is basically what I just talked about, and with the string and the integer optimization. And then the really cool thing is it can be jittered. That means the bytecode will be translated to machine code, and the inline cache will just keep a reference to that machine code. And if something changed, we just throw away the machine code and start over again from the unoptimized version. And for generating machine code, it's actually using a cool project called Llvm, a low-level virtual machine. So all Rubinius does is translate the Rubinius bytecode into Llvm intermediate representation. It's kind of the bytecode for Llvm, except it's not interpreting that. And Llvm then can translate that in the machine code specialized for your CPU. And it can also do a lot of optimizations. It can, again, do C-level inlining so that you do not have any jumps in there, which makes it run faster on the CPU, etc., etc. So that's really, really cool. There's not really like ARM-specific code or anything in Rubinius. Okay, still following? Nice. JRuby. We're nearly done. So there has been a lot of fuzz about something called Invoke Dynamic. Who in here, at the top of his head, can explain to me how Invoke Dynamic works? Okay. Who in here has heard of Invoke Dynamic? I mean, apart from that slide now. Okay, so half of it have heard of Invoke Dynamic, but no one can really explain what it is. Let me have a try at it. I can't promise, because it's really, really complex. I've written Invoke Dynamic code, and I still don't understand half of it. Generally, if you compile JRuby code to JVM bytecode on 1.6, it looks something like this. There's an invoke virtual here, which gets the JRuby call side, which is basically the representation of your method. Since the JVM does not know how to call Ruby methods on 1.6, JRuby has to wrap it in a call side. That call side has to land on the stack. So there's a method called a Java method, a JVM method, get call side 1, which is dynamically defined when you run your Ruby code. Then it's loading locals and self onto the stack. And then on that call side, it will call the method call, which as an argument will then get 2s. Oh no, not as an argument because the call side already knows that, but that will basically then do the 2s dispatch and call it. Now the cool thing with 1.7 is Invoke Dynamic. Invoke Virtual is the bytecode on the JVM that just calls methods. And on 1.7, you also have a bytecode for Invoke Dynamic, which changes the code to something like this. I cut out stuff, but so you have an Invoke Dynamic, and it just says call to s. So basically, the JVM now has an instruction called the method to s, but you don't know yet how you find to s. So let me tell you how to do that. So the Invoke Dynamic bytecode actually takes a ton of arguments. Those are the arguments JRuby needs, the execution context for the current thread, and the object at itself, and the argument, and it will return a Ruby object, iRuby object. In that case is what a Ruby object looks like from the JVM side. And also it's going to hand it a linker. And that linker knows how to explain the method dispatch to the JVM. And the linker has a bootstrap method. So the linker actually has 3 things. The linker has a bootstrap, a guard, and a fallback. And those methods are called by the JVM at different times. The first time the JVM comes to that point in the bytecode, which is the time where Rubinius would set up the inline cache, the JVM is going to call bootstrap on the linker, which would then do the equivalent of setting that up Actually, on the JVM, the bootstrap doesn't do much. It just calls the fallback again. Because now, and anyhow, so after the bootstrap has been called, the JVM will then see, do I have a call site here? And at that moment, there is no call site. The call site is basically what's called compiled code on Rubinius. So it looks at, do I have a call site here? If not, call the fallback. And the fallback actually then implements the Ruby method lookup and finds the call site for the method and places it there. And then the call site is called. Now the next time it looks at, oh, there's a call site here. So the only thing it needs to do is call the guard, basically asking, is everything still okay with this call site? And the guard then does the check that Rubinius had to do to where it looks at, has integer been modified? Is there a new 2s method for integer? And it says, no, everything is okay. And then the JVM can do that. And so the JVM can do all the inlining optimizations and basically checking if everything is okay. It's just one instruction overhead. So it's close to Java performance concerning the lookup. Okay. Did anyone, was that understandable? Okay, so the basic message, update the JVM and JRuby, get free performance boost. And that's my real last slide. Questions, or are you just waiting for lunch? "31 minutes. Oh, that says something different.
Questions?
None?
Come on. Oh,
That guy who's asking all the time, all the speakers.
yeah, I know.
So how do you feel about the fact that so we are generating bytecodes through Rubinius, and which are themselves fed into Llvm, which generate bytecode, which work the AST, etc. I mean, is there a general principle in there? I mean, all those levels of bytecodes and optimization for tree scaffolding, etc.
Yeah, there is a general, like that's how most VMs for dynamic, or that's actually I think how all VMs for dynamic languages work. And I think that's actually a pretty neat solution because that way, for one, like the startup time is really fast because you don't have to compile it right away to machine code. And all the abstraction makes it really nice. For instance, the bytecode compiler in Rubinius is completely written in Ruby. And you have the VM, which is the only part that's C++ that has no clue about Ruby, just knows how to run that bytecode, which makes it really, really, really easy to play with. And really, it's really nice for developers. There are a ton of experimental languages running on the Rubinius VM. And I've written experimental language stuff, both targeting Rubinius, the Rubinius VM, and the JVM, and it's just so easy on Rubinius compared to the JVM. I mean, there are probably way more optimizations in the JVM, but Rubinius is just developer heaven. And I really like the approach. I'm not sure, does that answer your question?
Yeah, so if I reformulate, you feel that each level of bytecode can allow different purpose, like Llvm will handle low-level deforestation or optimization, or...
Yeah. So the Llvm code is basically pretty close to machine instructions already, but platform independent. So that's why it makes sense to have that. Yeah, there's another question back there.
Hey, thanks, great speech. Would it be possible to just like pre-compile a Rails app, something else, into just native machine code and deploy that? Just inline everything and link?
It would be possible. The question is, would it be feasible? So you still would need actually the VM in that code, especially with Rails, because what Rails does is a ton of code generation during runtime, and that code needs to be compiled again. So it wouldn't actually buy you that much in that case. Also, you would have to compile in the whole universe, like all the dependencies, all the libraries, etc. Or actually, the code wouldn't be that optimized. What you could do is cache the different stages of compilation, which works really well for the bytecode stage, which is actually what Rubinius is doing, but not that well for any optimizations done to that, because basically once the system starts up again, most of that would have to be thrown away and wouldn't really buy you that much. But interestingly, like if you narrow the scope, if you say, oh, let's do that for projects where we don't have Rails, then that's actually something RubyMotion, for instance, is doing right now. We had the talk yesterday. So for certain use cases that is possible. In general, I don't think it's feasible.
Just quick note. So you said that Rubinius already caches the generated bytecode. So it's like in Python with PIC file.
Yes. Earlier versions of Rubinius used to store a .rbc file next to your Ruby file, but now there's a .rbx directory somewhere hidden on your system where the compiled code is actually stored, so that if nothing changed, it can skip the whole parsing, generating bytecode step.
Also for the standard library?
Yeah, especially for this. For the standard library, that is actually done proactively. That is done when you install Rubin. I'm not sure. Is it done for the standard? It's done for kernel. But it's still cached once you compile it the first time. But like the Rubinius kernel is compiled at build time. Okay, thank you.